Now F relates a line segment in the reference configuration to its map in the deformed configuration, whereas um, the strain measures, for example, the Green-Lagrange strain measure gives difference in lengths. So the Green-Lagrange strain tensor uh, does this. It takes the length of a line segment in the reference configuration and gives you the change in length, change in squared length of the line segment um, in the current configuration. Uh, or between the reference configuration and the current configuration. So it gives you the change in squared length between the reference configuration and current configuration of a line segment whose length is d capital X dot d capital X in the reference configuration. Similarly, other strain measures gives you different um, other relative changes in length. Now, there's another way to look at strain. Let us assume that we take the deformation gradient tensor and split it into two tensors by method which we will call polar decomposition of F. These two tensors are special. R is a proper orthogonal tensor, so it represents a pure rotation, and U is a positive definite tensor, which means that all the eigenvalues of U are positive, and also the eigenvectors. So for all V, uh, positive definite tensor, a positive definite tensor A will satisfy V dot AB is greater than 0. So this is what a positive definite tensor means. It also means that its eigenvalues are all positive. So how does that follow? So if I replace V, suppose this matrix A has eigenvectors n1 hat and n2 hat and n3 hat, then I will replace V by the eigenvectors. So I'll write n alpha hat dotted with A times n alpha hat has to be greater than 0 for a positive definite tensor, but A n alpha hat is lambda alpha n alpha hat, which is greater than 0, but n alpha hat dot n alpha hat is 1 because these are normalized, orthonormalized eigenvectors. Therefore, lambda alpha has to be always greater than 0, which applies for any alpha. Therefore, all the eigenvalues of a positive definite matrix are positive. So strictly positive, not even 0. So um, there are two ways of doing it. One, we can do a right stretch tensor, that means the positive definite tensor may appear on the right, or we can do it in a way which we call as the left stretch tensor, where the positive definite tensor appears on the left. These two tensors will in general be different, so we call one capital U and one small v. The left is called small v and the right is called capital U, and these have positive eigenvalues as we have proved. Now, when you do this, it's easy to see that C, which we had defined earlier as F transpose F, and remember the definition of C was it takes an element of length in the reference configuration, dots it, and gives you the squared length in the current configuration. So it's actually a measure of strain, and it was defined as F transpose F. And now it's easy to see that when you have split up F into, let's say, R times U, then F transpose is U transpose R transpose. F is R times U. R transpose R being positive, being a proper orthogonal tensor, this is equal to identity. So this gives you U transpose U, which we write as U squared. Similarly, you can show that B, which is FF transpose, comes out to be the square of the left stretch tensor. Also, recall that determinant of two matrices is the product of the determinants. Determinant of the product of two matrices is the product of the determinants, and determinant of A and its transpose are the same. So these two results will be necessary to prove what we want to prove. Then determinant of C is determinant of F and determinant of F transpose, but determinant of F and F transpose are the same. So this is determinant of F transpose square, which is equal to J square. So determinant of C is equal to J square. When we have a rigid body rotation, we will see that U's will be identity, and when we have a pure stretch, the rotation would be an identity. Now, what this polar decomposition does is it gives you a change in length in a slightly different way than we have done before. Suppose I have a line segment which is A naught in the undeformed configuration or reference configuration. It will map to F times A naught in the deformed configuration, and let's call this deformed vector as lambda. So this is in the deformed configuration, this is in the reference configuration. Now F we have split as, let's say, RU. So this RU times A naught gives you the deformed vector, and the length of this deformed vector is obviously lambda dot lambda. The squared length of this is lambda dot lambda. Let's call it lambda square, and that would become A0 transpose. So lambda transpose lambda is what we are trying to write. U transpose R transpose, that is the first lambda, and the second one remains as R times U times A naught, which again means that this is I, and you have A naught transpose U transpose U A naught, which can be written as U A naught dotted with U A naught. So the length, the squared length or the length, depends only on U, and the changed length of the stretched length of this vector A naught is simply U A naught. So if you want to find out its length, you don't need the R matrix at all. You can find out the squared length or the length by just using the stretch tensor. Similarly, similar results can be proved for V, which we are not proving here. Let's see a problem where this will become clearer. So in this problem, let's say we have a motion given by this. So you can see that this is a simple shear. We have done simple shear at the very beginning. So what this will do is, if you take a say 1 cross 1 square, as we always do, and apply this motion to it, this is x2, this is x1, and we are on a particular x3 plane. Let's say we are on x3 equal to 0, doesn't matter, or on planes it looks the same. So this will deform into something like this. So if you are on x2 equal to 0, then small x1 will remain equal to capital X1. So all points on this line remain as they are, but all points above it will shift to the right in a manner proportional to its height, the proportionality constant being 8 by 3. Now this is what is called a simple shear. Now let us get the f. So the f, of course, is this, easy to calculate. This is the f, and now we are going to do a polar decomposition of f. How do we do a polar decomposition of f? To do a polar decomposition of f, we first calculate c. We first calculate c, and why do we do that? Because we know that capital U square is equal to c. So if we get c, we can quickly get u square. So here's a motion, and you can easily see that this is a simple shear. How do we see that? Let's take any plane. Let's take x3 equal to 0 plane, and this is my x2 and this is my x1. And let us take a small square, 1 by 1 square, like we always do. And what you can see here is that this line does not have any motion at all, because this is x2 equal to 0, so this is equal to 0, and the displacements of this line are, all points on this line are 0, so this line doesn't move. Any line above moves in proportion to its height, capital X2, and the proportionality constant is this. So in the end, this will take a shape like this in the deformed configuration, and this is a simple shear. Now for a simple for this case, it's easy to find the f, and now we want to split f into r times u. So we want to do a polar decomposition of f, so we have to find r and u. In order to find them, we first try to find u. How do we try to find u? We make use of the fact that u times u is equal to c. We have proved this earlier. Now, if this is the situation and the eigenvalues of u are, let's say, lambda, and the eigenvectors are n, let's call them lambda alpha and n alpha. So there are three of them. Alpha goes from 1 to 3. Then to find the eigenvalues of u, we do this. We do say u times some vector n is equal to lambda n. This is the problem that we solve. Now multiply both sides by u. So you have u times un is equal to lambda un. Now u times un is another vector. So u times un should be equal to so un is again lambda n, so this would be equal to lambda square n, and u times un is equal to c times n, which follows from the fact that u dot u is equal to c. So what this shows is c has the same eigenvectors as u, but its eigenvalues are squares of u. So if we take the c, find its eigenvalues, we get the lambda squares. We take the square root of them and the eigenvectors, and we can transform that back to get my u. So this is what I do. I take the c and find its eigenvalues and eigenvectors. So the eigenvalues are 0.111 and 9. So these are the eigenvalues of so these numbers are my lambda squares. These are the eigenvalues of c that I have found, and square root of that are the eigenvalues of u. So this matrix contains the eigenvalues of u in the diagonal. The eigenvectors of c and u are the same as we have proved, and these are the eigenvectors corresponding to 0.111 and 9. These are the eigenvectors, normalized eigenvectors, and we have them in this matrix. So we now know from our linear algebra that if this is the eigenvector matrix containing the eigenvectors on the diagonal, and this is the matrix containing the eigenvalues, we can now transform this back to my x1 x2 coordinate system by doing simply NV n transpose. This is a result that you might have learned in your linear algebra course. So once you do that, you get your U. So to get U, again I repeat, to get U, you first get C from F, find the eigenvectors and eigenvalues of C. The eigenvectors of C and U are identical from this result. The eigenvalues are square roots of eigenvalues of U are square roots of eigenvalues of C. That's what we have used to find the eigenvector matrix, eigenvalue matrix, and the eigenvector matrix is identical for the two. And then we did this transformation to get U back in the x1, x2 coordinate system. Once we have got this back, then R is easily obtained by doing FU inverse. So R turns out to be this. Now, we have seen that this is a simple shear. We have convinced ourselves that the motion that we are given is a simple shear. So let us see in steps what is being done. Remember, d small x is F times d capital X, and F we have now split into a rotation and a stretch. So what we are going to do first is take every line segment in the body and do the stretch. So we will do only this part. Okay, we'll do only this part, and then we will do this R, where R is given by this and U is given by this. So first we will take a vector and multiply it by U to get the stretched part, and then we will rotate it by R, and this together, these two operations together should finally give me my simple shear. Let's see how it works out. On again, I start with a 1 by 1 square. 1 by 1 square. So I take each of these lines, and apply, say, this line. Let's say this line is simply E2. So I apply U times E2 to it and see where it goes. Okay. If I do that, this is what I get. So this is U applied to each of the sides, and that gives me this red parallelogram. Now to each of these red parallelogram sides, so I take this vector, let's say this is A, and I apply R times A. Similarly, so this is A1, let's say this is R times A2, and so on. I take these vectors and apply R to them, R being this matrix. So I apply the pure rotation to each of the sides, and when I do that, I get back this black parallelogram, which shows that this has the final motion is a simple shear, but the pure stretch brings it here, and the pure rotation just rotates it back to this. So this black one is just a rotated version of the red one. So this is the way we split up the rotation and the stretch in at a material point. So to use the concept of polar decomposition effectively, which we will need to do when we learn about hyperelastic materials later in the course, we need to understand the Cayley-Hamilton theorem, which you may have studied in your linear algebra course. What the Cayley-Hamilton theorem says is that the matrix itself, for which you are trying to find the eigenvalues, in our case the matrix, the tensor, second order tensor U, satisfies its own characteristic equation. Now here's a problem where we use the Cayley-Hamilton theorem to find an explicit expression for U in the special case of a two-dimensional motion. So in a two-dimensional motion, U is a second order tensor which has 4 components, and its characteristic equation is as usual given by this. So it has only 2 invariants, I1, which is the trace, which is simply u11 plus u22, and I2 which comes out to be this for the two-dimensional case. Remember, I2 is trace of u whole square minus trace u square and half of that, or the other way around. I think it's minus here and plus here. Okay, so this is I1 and I2. This is for the two-dimensional case. Now, by the Cayley-Hamilton theorem, u should satisfy this equation. So if I replace lambda by u, this is what I will get. This is what I will get. U has to satisfy this equation. And since u square is equal to c, we have proved that already, then you get directly an expression for c in terms of u. So u is u is 1 by I1. So I take c and I2 to the other side, and there should be an I here. There should be an identity here because all the terms are tensors, so there should be an identity here. So then this is the u that I get. Now I1 can be easily determined. It's a trace of u. And the trace of u, since u is this, trace of u would be trace of c plus I2 times trace of I, which is in the 2D case just 2. Okay, so from here we have an expression for I1 in terms of c. Similarly, I2 is determinant of c to the power half. We have again proved this result because c is equal to u square. Determinant of c is the square of the determinant of u. So this follows from there. Okay, and now putting these together into this expression, we can write an explicit expression for the u in terms of c for a two-dimensional problem. As we have mentioned in the previous problem, c is easier to find if you know f. You can find f transpose f, and from that calculate c. That's easy. And once you know c, you don't have to solve the eigenvalue problem explicitly. You can use this expression directly with c to find your u. You don't have to go through the route that we took in the previous problem where we found the eigenvalues of c, then form the eigenvalue matrix for u with the information that eigenvalues of u are square roots of eigenvalues of c, and then the eigenvectors are the same. Then do the transformation to get u in the xy coordinate system, x1, x2 coordinate system, and then from that find r and so on. That's the route that we took in the last problem, but we don't have to do it if we have if we have this expression directly in terms of c. We don't have to find the eigenvalues anymore. However, for 3D this may not be possible. Finding an explicit expression may not be possible. So in 3D problems, you may still have to go through the eigenvalue eigenvector route. You might have to find the eigenvectors and eigenvalues of c first in order to get u, like we did in the previous problem. Now here is an interesting problem. This is a triangular element, a linear triangular element, T3, at time t equal to 0, that is in the initial configuration. And now this is part of a body which is deforming in some way, and I know how these nodes are, the nodal coordinates are flowing through time. So I know that x1 has x1 and y1 have time dependencies given by this, x2 and y2 by this, and x3 and y3 by this for this particular triangular element, and I am supposed to find the stretch tensor at each of these time points, t equal to 0, t equal to 0.5 and t equal to 1. Now since x1 and y1 vary according to according to this motion, I can plot out the values of this at time t equal to 0. At time t equal to 0, this is a and this is 0. So 1 is here. 2 is 0 and then 2a. So 2 is here and 3 is at 0, 0, 3 is here. Similarly, at t equal to 1, I can put 1 here. This will be 3a. So this point is at 3a, 2a, 2 is at 2a, 0, 3 is at 3a, 0, and similarly I can do it for t equal to 0.5. Now at these locations, for any point inside this triangle, at these time points, at any point inside this triangle, I want to find what is the stretch tensor and probably the rotation. So to do that, what we have to realize is that for any generic point inside this element, the coordinates are given by interpolations of the coordinates of the nodes and the interpolation functions or the shape functions, which in case of this element are the area coordinates. We have learned that in our finite element course. So for any point, x and y are given by the nodal values of x and nodal values of y at the three nodes, and the shape functions, which we call zeta 1, zeta 2, zeta 3. These are area coordinates, and the sum of the three shape functions is equal to 1. This is also a property that shape functions obey. Now, in the initial configuration, now we want to find capital X. So for any point here which has coordinates of capital X and capital Y, we will take the x1 at time t equal to 0, and that will give me my capital X and capital Y. So x at 0 and y at 0 are here. So x1 is a0. So for x at 0, I write x1 at time t equal to 0, which is a. So a zeta 1 plus x2 at t equal to 0. x2 at t equal to 0 is 0. x3 at t equal to 0 is 0. So x at 0 is simply a zeta 1. Y at 0, on the other hand, y1 at 0, y1 at 0, y1 at 0 is 0. y2 at 0 is 2a, and y3 at 0 is 0. So this simply is 2a, and y at 0 is zeta 2. So this is my capital X, and this is my capital Y. This is because t equal to 0 is the initial configuration. Now let us take the situation at t equal to 1. So let us take the situation for this configuration. For this configuration, so let me erase this. For this configuration, x1, x2, x3, let's note it down. x1 is 3a, 2a, and 3a respectively. So this is 3a, this is 2a, this is 3a, right? And y1 is 2a, 0, and 0. So y1 is 2a, y2 is 0, y3 is 0. Plug it into this, then you get x of 1 is equal to x1 3a zeta 1 plus 2a zeta 2 plus 3a zeta 3. And from the initial configuration, we know that zeta 1 is equal to capital X by a, zeta 2 is capital X, capital Y by 2a. Therefore, zeta 3 from here is 1 minus x by a minus y by 2a. So this is my zeta 1, zeta 2, zeta 3 in terms of the initial configuration, initial coordinates. And if I replace zeta 1, zeta 2 and zeta 3 by this, I get a relation between the x coordinate at time t1 and the initial coordinate. So this actually defines the x part of my motion. Similarly, I can do it for the y part. So y at 1 is y2, y3 are 0 and y1 is 2a. So it's 2a zeta 1, which is 2a into capital X by a. So it is 2 times capital X. So this is my motion at time t equal to 1. And now I have a relation between small x y and capital XY, and from here I can find the deformation gradient and then carry out the deformation gradient is this, and then C can be calculated from here, and when you calculate C, you get a diagonal matrix. Since C is diagonal in this case, just by chance, these are the eigenvalues of C. Remember, eigenvalues of C are the squares of the eigenvalues of U, and C is diagonal, so the eigenvectors are 1, 0 and 0, 1 respectively, and the eigenvalues of U would be square roots of this, so there would be 2 and 0.5. This is a rather fortuitous case because I get a diagonal C, and then I can get the R by just doing FU inverse, and that gives me this, which is a counterclockwise 90-degree rotation. Since your C comes out to be diagonal in this case, this motion is easy to understand. Remember, F is R times U, and you first apply U, which is you stretch things 2 times in the x direction and compress them by half times in the y direction. So if you go to your initial configuration, so these dimensions you double them, and you half it here. So 2 comes somewhere here, 1 goes somewhere here. You have stretched it by 2 times, and this is your triangle. And then you have a counterclockwise rotation. So you rotate this whole thing this way to get this configuration, which is stretched by 2 times in the x direction, compressed by half in the y direction, and then turned by 90 degrees. That's when you get this. 1 comes to the top, 2 comes here, and 3 remains where it 3 moves to the right. Okay. Now we do the same thing for point t equal to 0.5, but in that case the coordinates of t equal to at t equal to 0.5 are different, and therefore the motion, the functional form of the motion will be different, f will be different, and so on. So this would be your x and y at t equal to 0.5. You can verify this. And here again, I have written small x and small y in terms of capital X and y, which immediately would give me u square, that is C, which is F transpose F, as this. So I calculate F from here, do F transpose F, and this is what I get. This is no longer diagonal. This is no longer diagonal, and so you will need to now find the eigenvalues of this. So these are the eigenvalues of C, and sorry, the squares of these are the eigenvalues of C, and these are the eigenvalues of U, and these are the eigenvectors of both C and U, and you do the transformation to get now U in the uh, in the xy coordinate system, and as usual r is fu inverse. So do that do that calculation and make sure that you get this shape, which is again some kind of a rotation, and it is a combination of a rotation and uh, um, and a deformation. So there's a stretch and a rotation involved of this element in order to get this.